Hey guys. So last week we figured out how to calculate the temperature of the planet strictly due to the amount of energy that was coming from the sun. And we found that that didn't actually work for Earth. Earth is actually too cold to be habitable based strictly on the amount of energy that it's receiving from the star, from our sun. So something else is going on, and hopefully you figured out that our model does not take into account the effect of the atmosphere. So the atmosphere is actually kind of like a blanket on the Earth. It's trapping heat in the atmosphere so that the atmosphere gets a little bit warmer, which of course then warms up the surface. So this is called the greenhouse effect. Now you've heard a lot about the greenhouse effect lately. A little bit of a greenhouse effect is a good thing. Without that greenhouse effect, Earth wouldn't be habitable. Too much of a greenhouse effect is a bad thing. This is what happened to Venus. Venus was a victim of the runaway greenhouse effect, and we'll talk about that later on. So, what we need to do, if we want to figure out the surface temperature of the planet, we also need to include the effects of the atmosphere. So, we talked about how the effective temperature is just the minimum temperature. The atmosphere can actually increase that a little bit. So you could have a planet that would normally not be habitable, but if it's got a thick enough atmosphere providing enough greenhouse effect, it could actually raise its temperature just enough to put it into that Goldilocks range, and you found your habitable world. So today what we're going to do is our goal is to figure out how much temperature gets added by the atmosphere. Then you can figure out, if it's plus 30 degrees, plus 100 degrees, whatever it is, you can add that to the effective temperature, and now you've got your surface temperature. And that's what we're going to be putting into the water phase diagram from here on out. Okay, let's get started. Okay, so you calculated for your practice, you figured out the effective temperature of each of these planets. And we see that there's a mismatch between the actual temperature. So Venus, for example, has a temperature of 184 degrees. That's its effective temperature. That's very cold. But Venus itself is actually 735 degrees. It is much hotter than it should be. So a lot of people say, oh, well, Venus is hot because it's closer to the sun. It's not actually true. I mean, it actually would still be fairly cool, but its actual temperature is so much higher because it has that atmosphere. Earth, we figured out its effective temperature was 254 degrees, which is just a little bit too low for it to actually be habitable. But the actual temperature is 288 degrees. So this ends up putting it right in that habitable zone. Mars, its effective temperature is 210 degrees, but its actual temperature is 220 degrees. So it's still quite cold. It's still too cold to be habitable. But if you look at the temperature differences here, the difference between the effective temperature and the actual temperature, what do you think makes the largest difference? Mars has only a small difference. Earth has a medium-sized distance. Venus has a huge distance. It's the atmosphere. Venus has an incredibly thick atmosphere. It's 90 times thicker than it is on Earth. If you were to try to stand on the surface of Venus, you'd be crushed like a bug. So this is like, pressures down at the bottom of the ocean from that. So its atmosphere is extremely thick. It's also mostly carbon dioxide, which is a great greenhouse gas. And so it's trapping that heat. And in fact, it's adding almost 600 degrees to the temperature. So it's hotter because of the atmosphere. Earth has Earth's normal atmosphere, one atmosphere. And so it's quite a bit thinner than Venus, but it's still thick enough that it's trapping quite a bit of heat, 30 degrees or so. And so that's raising our temperature, and that's putting us in the habitable zone. Mars actually does have an atmosphere, but it's very, very thin. It's better than any vacuum we can actually make on Earth. But it's got weather, it's got clouds, it's got things like that. So that is raising the temperature just 10 degrees, which Mars would need quite a bit more. So this is actually why one of the ways to terraform Mars is to melt these ice caps, which are mostly carbon dioxide, turn them into vapor, have that go into the atmosphere. That'll trap more energy, and that will raise Mars's temperature, maybe enough so that we could have liquid water on the surface, and then Mars would be habitable as well. So what we want to do is we want to figure out, how do we get this distance? How do we know when it's 600 degrees? How do we know when it's 30 degrees? And how do we know when it's 10 degrees? And the difference is going to be based on the percent absorption due to greenhouse gases. So let's look at that. So when we look at Earth's atmosphere, as we mentioned, is 78% nitrogen. It's almost all nitrogen. That freaks people out. What's in your room right now is basically nitrogen gas. The vast majority of it, over 3/4 of it, is nitrogen gas. Only about 20%, 21% of the atmosphere is actually oxygen that you're using. So people are saying, I can't breathe, I need oxygen. Well, that's because you're not breathing, you're not using the nitrogen to get energy out of. but most of the atmosphere on Earth is actually nitrogen. You are swimming through nitrogen gas. There are a few other things. The next most common element is argon, which is a noble gas that's providing stability to the atmosphere because it doesn't react with anything, only about 1%. And then there are some very tiny, tiny amounts of water vapor and carbon dioxide and a few other things in the atmosphere. Just these tiny amounts account for all of that increase in temperature. And that's what's doing that is by the greenhouse effect. So we talked about how we measure atmospheric pressure is 1 atmosphere. Another term that you'll hear is 1 bar. 1 bar is equal to 1 atmosphere. They're the same thing. If you've ever heard of barometric pressure or a barometer, that's something that's measuring the thickness of the atmosphere. So you're going to see both of these terms. I'll be generally using atmosphere because that's what most people understand. But you should be confident when you see bar. Just tell your brain that's just atmospheres. Okay, so some gases allow light to come through. And so it might allow, all the visible and all the infrared and all the ultraviolet to come through. So that means it transmits. Others absorb it. So, for example, the oxygen in our atmosphere, our normal atmosphere, might allow all of the visible light to come through. But if it's got carbon dioxide in it or water vapor, both of which are greenhouse gases, they transmit the visible light, but they absorb the infrared light. So it can be different depending upon the types of light that's coming in. So if it absorbs some of that light, then that's going to increase its temperature. If you think about it, that makes sense. That energy has to go somewhere. So if that energy is getting absorbed in the atmosphere, the effect is to raise the temperature of the atmosphere. Now, I want to pause here just a minute and make sure that everybody's not getting confused, because you've probably heard of the ozone layer and the problems that we have with the ozone layer. There's a big hole in the ozone layer over the Antarctic. And if we were to lose our ozone layer, we would all die. But this is a different way that the universe is trying to kill you. This has absolutely nothing to do with global warming. It's not related to global warming at all. It is a different thing. So ozone actually absorbs ultraviolet light. And so that's keeping all this dangerous ultraviolet light from the sun from making it all the way down to the surface. So it's composed of O3, and we don't need to get into all the details about how it works, but when it absorbs ultraviolet light, it breaks apart this O3 molecule into O2 and free oxygen. Then later on down the chain, we won't get into the details, but later on down the chain, that oxygen then recombines with the O2 and forms another layer of ozone. And so our ozone is being continuously replenished, which allows it to continuously block that UV light. So there was a material called CFCs, and these are generally used as propellants or refrigerants. Freon is a CFC, things like that. The thing is they bond more strongly with that free oxygen than the O2 will bond with it. And so the CFCs steal the oxygen, that free oxygen. So the O2 has nothing available for it to turn back into ozone. And so over time, CFCs were actually depleting the amount of ozone in our atmosphere. And this is a map of the southern hemisphere. You can just kind of barely see. This is Antarctica right here. And this is showing how little ozone we had. And it actually extended basically all the way up here to South America. So this was starting to be a problem. If we lost our ozone layer, then basically this planet would be completely uninhabitable, because the UV energy from the sun would just sterilize the whole planet. We'd all be dead from skin cancer within 10 years or so. So the Earth almost died in around 1990s. So all the nations of the world got together and they voted to ban CFCs. This is the first and so far only time that every nation in the world has gotten together to actually save the planet. And so all CFCs were banned. We started finding replacements for them. And now this ozone hole is not gone, but it is at least getting smaller. So we seem to have averted the extinction of all life on Earth from that. Global warming, on the other hand, is a different way that the universe is trying to kill you. And so here's basically how the greenhouse effect works. We've got this energy that comes down. Some of it gets absorbed by the Earth and then gets re-radiated as infrared. Now, some of the energy coming from the sun is infrared, and so it gets stuck. Some of it is actually going to get absorbed in the atmosphere when it gets stuck there, and then the atmosphere will come and reflect it down. Some of it is going to be visible light, and it's going to pass all the way through. So some of it is going to reflect off the surface off the atmosphere itself, and it's going to get reflected back out into space because our albedo is not zero. We actually do reflect some of the things. On the other hand, the Earth itself is warming up, and so if you were to calculate the temperature, remember we can use Wien's law to calculate the temperature. Using the temperature of the Earth, we're going to find that the Earth is emitting mostly infrared. Some of that energy is going to escape. Some of it is going to get trapped in the atmosphere. The atmosphere then heats up, and based on its temperature, it's also putting out infrared. And so that some of that infrared comes down and warms up the planet, makes the planet warmer than it would have been. Some of it escapes into space. So what we need to do is we need to look at the balance between the amount of energy that we see coming in from the different locations. All right. So look on your energy balance sheet here. Also, there is an additional page for this that you can have printed out and have separate. It looks like this. There's nothing to write on here. This has just got all your charts and tables, but it also has all the numbers that are going to go on these arrows. So let's do the first one together, and then I'm going to have you pause the video each time to answer these. So it says, add up all the arrows that leave the atmosphere. What is the total energy emitted? Okay, well, when we look at our diagram here, this arrow is leaving the atmosphere, this arrow is leaving the atmosphere, this one is, and this one is. So take your calculator and go ahead and add all those up. And I'm going to do that with you. So for this one right here, if you look at it, it says there are 30 watts per square meter. For this one right here, looks like there's 77. So I'm going to add those two. Right here, looks like it is 40. And right here, that looks like that's going to be 195. And so I get 342 watts per square meter are leaving the Earth's atmosphere. Is that what you get? All right. So then the second question then says, in that section, compare that value to the energy from the sun. Is it greater than, less than, or equal to? So the amount of energy coming from the sun is the amount of energy in this big thick arrow right here. How much is that? Well, looking at it, it's exactly 342. But you knew it had to be that, right? From the lab last week. We know that 100% of the energy going in has to come out. So however long, whatever happens in this atmosphere, the amount of energy that's escaping equals the amount of energy that's coming in, as it should. All right. So now what we want you to do is look at the energy that is, so comparing, they're going to be the same. So now Earth is in energy balance. So now let's look at the energy that's being absorbed by the Earth. Those are just the arrows here that are going into the Earth. Pause the video, add those up, and let's see what you get. All right, looking at our chart then, we want to do the amount of energy that's being absorbed into the Earth. So we've got 168 from this one. Oops. So 168 plus the other one over here is 324. And so I get 492 watts per square meter. Is that what you get? All right. So compare that then. And is that equal to, greater than, or less than the amount of energy that we're getting from the sun here? Well, this one's only 342. So the amount of energy going into the Earth is actually greater than the energy that we're getting from the sun. That means something else is giving us some energy. And hopefully you can see that something else is going to be the atmosphere that's feeding in here. All right. So where does most of that energy come from? Is it coming from the sun or is it coming from the atmosphere? Compare the two numbers here. Which of these is bigger? The yellow one, which is coming from the sun, or the red one that's coming from the atmosphere? We're getting most of our energy in infrared from the atmosphere right here. Okay, and if you're not sure about why, just look at the numbers. The energy coming from the sun is 168, and the energy from the atmosphere is 324. Got the pattern now? All right, now we want to look at the total energy going into the atmosphere. You know what to do now. We're looking at the ones that stop at the atmosphere. So this one and this one are the ones that stop. Add them up, see what you get. Okay, what you get? So when I add these up, I get 519 watts per square meter. Is that what you get? So now compare this to the value from the sun. Is it greater than, less than, or equal? Well, it's quite a bit more, right? It's quite a bit greater. Now, where does most of this energy come from? Is it coming from the sun or is it coming from the earth? What is contributing to warming the atmosphere, the sun or the earth mostly? You're going to find that this one's bigger, right? And so this one is actually producing most of the energy that's heating up the atmosphere. It's actually coming from the earth. Okay, so what's happening here then, we talk about this, that the light from the sun is heating up the earth is then re-radiating that into the atmosphere and it's getting warmer. Okay. So how much warmer is it? Well, to figure that out, we need to figure out the greenhouse percentage. How much of that is being absorbed by it? Now, the problem with this is that we're looking with a telescope out into space. I can't go down to the surface and actually measure the temperature, how much is going into the planet right here, which is what I really want. But I can figure it out based on what percentage is being re-radiated out here into space. So what you can do then, the technique we're going to use is we're going to look at what is the total amount of energy being emitted into space. Okay? What is the total amount of energy, emitted by the atmosphere into space? So only this part right here is going to be emitted by the atmosphere into space. And that's what I can detect. So only this one right here. This one's being emitted by the earth. These are being emitted by the sun, right? So this one is the heat from the atmosphere going into space. And I can measure that using my instruments. So what do you get? You just look it up. There's no addition. Right, so that one's going to be 195. So this gives us a measure of how much is actually being absorbed on the planet. Because if the planet is getting hotter, then the atmosphere is getting hotter. And I can see that by how much extra energy the atmosphere is putting out. Because all of that has to ultimately come from the Earth from that. Okay, so I've got 195 watts per square meter being put out by the atmosphere into space. If I want to figure out the total percentage, all I need to do is take this number and divide by this number here that's coming from the sun. And we decided that that was 342. So I'm going to do 195 divided by 342. Do that with me. 195 from here divided by 342 here. And I get 57%. Remember, you multiply by 100 to turn it into a percentage. Now, in your project, you're not going to actually have to calculate all this. We're going to give you the percentage. The computer, the simulator is actually going to calculate it for you based on its observation of the atmosphere that's coming in. So we're going to give you a percentage. What you need to know is how much is the temperature increasing given this certain percentage. So look on your chart down here, right here on the side. This is also on your equation sheet so that you can find it. If we are from 50, if we're at 57%, we're between 40 and 60%. So that means that the temperature is going up, the surface temperature is going up 30 degrees, roughly. And that's a pretty good estimate. So our effective temperature on Earth is 254 degrees. The greenhouse is adding an average of about 30 degrees, which puts our total Earth surface temperature to 284 degrees. Just add them up. 254 plus 30 is 284. Now, go into your water phase diagram, and I want you to figure out what phase should water be if I have 1 atmosphere and 284 degrees Kelvin. Pause the video until you've got it. So you go up with 284 to 1 atmosphere, and sure enough, we have a liquid water. So it's our atmosphere that's enabling Earth to be habitable. It's increasing our temperature just enough so that we're able to maintain the temperature that we have. Okay. So this kind of works like a sink. You know, if there were no atmosphere, then the water in would equal the water out, right? We don't get an overflowing sink. On the other hand, what if I put a bucket in here? It will fill up, and so we've got more water, more temperature in our sink area. But then eventually it overflows and the rest of it comes out. So the total amount going in equals the total amount going out. But for a little while longer, I'm able to store some of that water, some of that temperature in the atmosphere. And this effect, the atmosphere is acting like that bowl that's allowing this to keep a little extra heat in the atmosphere. So the total in still equals the total out, but because it spends a little more time in the atmosphere ends up staying warmer. All right, so if we know the percentage, this is just reviewing what we did before. If our effective temperature is 254 degrees and our greenhouse temperature was, our greenhouse temperature was plus 30 degrees, you add that in there and you're going to get 284. Okay. So now the next question is, what two types of light is most of the energy coming from? So most of the energy from the sun, what two types of light are going to be coming from the sun? Just look at the table. What are the two largest percentages? That's going to be visible and infrared. Do you see that right there? But the Earth then is re-radiating it. What is most of its energy coming from? It's mostly infrared. So this is why we're interested in gases that are trapping infrared light. Visible light, it's going to go on through. The infrared is getting trapped by these greenhouse gases. So we define a greenhouse gas to be any gas that absorbs infrared light. Any gas that's going to trap infrared light. It's going to allow the visible to come through, but it's going to trap that infrared light. So when you look at the list here, these are the gases that are in Earth's atmosphere. What are the three strongest greenhouse gases? What are the three most common greenhouse gases in Earth's atmosphere? You just look at the percentage absorption here. So carbon dioxide is a big one. Water vapor is also a big one. Water vapor actually traps more infrared. It's a stronger greenhouse gas than carbon dioxide. This is actually what killed Venus. We'll get to that a little later. Methane is also a very strong greenhouse gas, but nowhere near as strong as carbon dioxide and water vapor. Most of the methane in Earth's atmosphere is cow farts. So roughly 90% of the methane in Earth's atmosphere is produced by bacteria in cows' digestive tracts. So that's getting broken down in the atmosphere by sunlight, though, but it's getting continuously replenished by the life on Earth. So that's why it's so small. Carbon dioxide and water vapor then account for most of the greenhouse gases in our atmosphere. So water is actually the strongest. Well, we don't want to get rid of all our water, right? We need that water. We need that water vapor. We need that humidity in the atmosphere. The other thing is that absorption by water is strongly temperature dependent. So it depends upon, how much of what the temperature is going to control how much infrared it's going to absorb. If the temperature is at one end of the scale, we're not going to get as much absorption. If it's the other end, I'm going to get a whole lot more. So that's variable. But there is one gas that always, no matter what, always absorbs lots and lots of infrared. And what is that one? Well, that's going to be carbon dioxide. So you've heard us talk about, carbon in the atmosphere. For the most part, we're talking about carbon dioxide. Carbon monoxide and things like that will also be greenhouse gases, but they're not as strong as carbon dioxide itself. All right. So look down on the last part of your class notes here. So it's asking, what is one way that this gas is increasing in our atmosphere? Can you give me an idea? Well, fossil fuels are actually probably the most common way, because you're taking the carbon that was in the ground and you're burning it, and then that's putting that carbon that used to be in the ground is now in the atmosphere. That's the key. As long as the carbon stays locked up in the ground, who cares? It's not doing anything to us. But as soon as you burn it so that you're putting it in the atmosphere, now you're increasing the amount of greenhouse gases. And we've seen that right now there's just a trace amount of carbon dioxide in the atmosphere, and it's causing all of the effects that we're seeing right now. Now, if we significantly increase it, then those effects are going to be even stronger. And we'll talk about that next time. So if the gas increases, what's going to happen to the Earth's surface temperature? It's going to increase as well. Okay, so now you see why carbon dioxide is probably the strongest greenhouse gas. It's not the only one. And so if we've got an alien world that's got methane, it's got water vapor, that's going to be increasing the temperature. And so we can figure that out based on once we figure out what elements are present in the planet's atmosphere. And one of the things that you're going to do as part of your project is you're going to look at a spectrum. Remember how we were able to match up the fingerprint to identify the different gases? Well, we'll do that with our line spectrum. We'll be looking at dips. And you just play a little game. You'll just say, okay, if I turn on carbon dioxide, what does it look like? And then you're going to try to match the two. So you're not going to have to go referencing numbers. You can just sit there and try different combinations until you've exactly matched that spectrum. That's going to tell you what gases are present. Then based on the gases present, the simulator knows the greenhouse strength of each of those gases. It will actually calculate the absorption percentage for you. All you need to do then is go into the table, and you'll be able to see how much the temperature is going to increase. That'll give you your final surface temperature. Always remember, it's the surface temperature that should be going into the water phase diagram, not that effective temperature. It would only be the effective temperature if there's no atmosphere at all from there. Okay? All right, so take a look at that, and then next time we'll get into some of the effects with this. We'll see you then.